Is it possible to see the?
Yes, sir. Can you share the screen, sir?
Is it visible now?
Not
Hello?
yet, sir. Not yet, sir.
Not yet. Okay. Can you see now?
Yes, Professor. Yes.
Okay. Oh, so I'll start.
Yes, sir.
Okay. In the last 3 lectures, we have been very leisurely going through the developments of 1900 and 1905. And of course, if we go at that pace, then of course it will take some 25 more lectures to reach the development of quantum mechanics since 1925. So what I'll do is just take a few points at here and there and give you an idea of general progress, because after the Einstein's 1905 paper, there was controversy. Even Planck did not believe that energy of radiation was quantized in lumps or kind of particles of h nu, and this remained the major concern for all physicists till about 1923-24, when experimental evidence in favor of photoelectric effect and all other kinds of effect which were predicted by Einstein in 1905, they were confirmed. Still, the uneasiness persists. And even today, there are people who might think of photons as some kind of particles, and at the same time worry about how will 2 different photons interfere with each other. How does one explain the interference effects of photons? This even today is a very active subject, and the difficulty in doing that is that it has both a wave-like nature and a particle-like nature. And please remember what I told about Einstein's contribution in 1905, and one more paper I will discuss very briefly today. Einstein used the limit of Wien's law, that is higher frequencies. That is the quantum limit, not the classical limit. And in that high frequency photons, they do behave like particles. You can think of X-rays and gamma rays. Gamma rays are generally thought of as particles, and nobody talks about their interference patterns. The reason is that the wavelengths are so small that it may not be possible to observe them, those interference effects, but they are there at all frequencies and all wavelengths. So initially there was great resistance to accept these ideas. At the same time, there was this history of spectroscopy, which Niels Bohr and other people in Rutherford's lab in England, where Niels Bohr was working, they were worried about, because the light which comes out from atoms when they are heated, not only apart from the spectrum which is black body radiation, there are very bright lines and also absorption lines in the spectrum. It was discovered by Fraunhofer in the middle of 19th century that light coming from from sun, when you observe it carefully, there are dark lines, which means as if that light has been absorbed somewhere and is not available to us. So the spectroscopy was one thing where you don't have a continuous spectrum, but very characterized, very particular frequencies or wavelengths were available. And therefore, this is something which Niels Bohr and other people around that, they were there. So the question at that time was, how does an atom radiate? And for that, you need a model of the atom. And there were two models at that time popular. One was the Thomson model, and the other was the Rutherford model. Thomson model was like a distribution of positive charge in a continuous manner and an electron going inside it. And the Rutherford model was that the positive charge in the atom was in a very small volume located at the center, and the electrons were going around it or oscillating about it. So Niels Bohr did not believe in it, and Thomson model was given up for other reasons also, like scattering experiments, which Rutherford also did. And Rutherford's scattering of gold by alpha particles, which were coming out of radioactivity, they showed that the center of the atom is a single point charge of positive, and therefore that kind of put evidence in favor of Rutherford's model. So Niels Bohr's idea was to take the Rutherford model of atom, and then he assumed that the electrons around it going around in like planets around the sun, they cannot exist for all the distances or all the energies, because if you consider an electron at that small region, like 1 angstrom or size, and going around like this thing, you can use the classical theory of radiation and find out that it will radiate away all its energy in no time at all, something like 10⁻⁻15 seconds or something. So this is not possible for electrons to be going around the atom and also use classical mechanics. So the classical mechanics therefore had to be, it doesn't seem to hold there. So Bohr simply believed that there is energy of the electron going around the nucleus, but it doesn't radiate. And these he called as stationary states or stable states. And then whenever there is a transition between two energies, two such states, then he used Einstein's formula that radiation will come out in the form with frequency which is given by the difference of these energies. This is the first time when he uses this difference of energies as the frequency, determining the frequency of the radiation. And another ingredient in his theory which was just a little before was discussed by Ehrenfest, saying that the angular momentum is a integral multiple of h over 2 pi. The reason for that I will discuss a little later, but the whole point is that h has the dimensions of energy into distance, which is the dimensions of action. And that's why h was known as the quantum of action. And whenever there is a physical quantity which corresponds to action, people would have thought that it is something which can only occur in multiples of this basic unit, or the quantum of action as it was called. So for slow vibrations, and the fourth point which he believed, and something which was very important later on, was that for slow vibrations, after all, we also know that charged particle going around another charged particle in a circle, they also radiate classically, and classical mechanics seems to hold very well. No, maybe not at very short distances, but at larger distances, it seems to hold very well. So he wanted to find that there is a limit in which the radiation which is going around the atom, nucleus of the atom or the central charge will correspond to what is expected classically. So I may not be able to go to all the details, but these are the four assumptions with which he started. So let's see what are the kind of things that he said. If suppose there is a circular orbit of radius r with a charge of plus e at the center, as we would expect for Rutherford atom, and it's hydrogen atom, so there is a plus e at the center and minus e going around with velocity v, then there are these three equations you can immediately write. One is that the force, Coulomb force of attraction between positive and negative charge, if it's a circular orbit, it should explain equal to the acceleration towards the center, which is mass times v square by r. This is the centripetal acceleration. This should be equal to the force. And the second thing is what the Ehrenfest law of the quantity of action being integral multiple of h. Now here, of course, since it is moving with velocity v, mass times velocity is the momentum and r is the distance. So mv into r multiplied by 2 pi r, which mv, which is p, multiplied by the distance that it has in one circle, going around one circle, is 2 pi r. That is the quantity of action, and which should be equal to n times some h, that is the Planck's constant, that is some integral number of times the quantum of action. So, and the third equation is of course the energy equation. The energy of that particle electron going around is half mv square, which is the kinetic energy, minus 1 upon 4 pi epsilon 0 e square by r, which is the potential energy. Potential energy obviously is negative because it's an attractive force, and charge E and minus E are multiplied. So these are three equations in which V and R can be eliminated. So if you do that, you'll get an answer which is just a very simple calculation, that En is equal to some constant here multiplied by 1 upon n square. And therefore, if you take the difference of energies of En and Em, then the constant will be equal to 1 upon m square minus 1 upon n square. But because of this minus sign, m being smaller, it has a larger value, and n being smaller. So this is h times nu of Nm. That is, if the energy at nth level falls into the level at m, then this will be the frequency determined by the difference. Now, this was very well verified, at least at that time. The hydrogen, at least 4 or 5 of hydrogen spectral lines were known, and these seem to completely satisfy the lines which are there, initial lines of the Balmer series. The Balmer series corresponds to m equal to 2. That is, the second level, third level falling to second level, and fourth level falling to second level. It's not the ground state. It's not, they are not falling to the ground state because that energy is larger and they were not seen at that time. So the Balmer series can be explained, and also the combination principle, which had been discovered in 19th century by various people, and very complicated formulas were found to find out some kind of a pattern in the spectral frequencies. And actually, it was a very important development that people found that it's not the wavelengths which are simply related, but it's the inverse of the wavelengths. Whatever it is this frequencies differences are such that if you add En minus Em to Em minus Er, then that will be equal to En minus Er. That is, this frequency and that frequency, if added together, will give you the third frequency. That is called the combination principle, and it also automatically satisfies that. But of course, Bohr's theory had weaknesses, and one is that it does not explain the spectra of other complicated atoms. It might explain a few of those ionized atoms where you have just one electron going around the nucleus of another. But when there are other electrons, there is interference between them and spectra becomes far more complicated. And of course, this is another thing which occupied people's mind for a long time, which is this, that only frequencies are determined by the Bohr theory, but intensities of lines are not available. So the point is that if radiation is coming out, you want to find out not only the frequency of the radiation, but also the intensity. And it is seen that intensity of different spectral lines is different. So there must be a way of finding this out. So that was not available. Now, about this intensities, there was a contribution from Einstein, which is a very simple and, as Einstein always, very clear paper of 1917, in which he makes a few assumptions. And that is that atoms have discrete levels of energy, that of course everybody believed at that time. Secondly, that in the presence of radiation of intensity, transitions take place, which is also something understandable, because the presence of radiation will cause absorption or emission also of frequency. It will catalyze absorption as well as emission. And third is that there is a spontaneous emission. This is Einstein's major contribution, to say that even when there is no radiation from outside acting on it, it will automatically go from one state to a lower state. And that is the spontaneous emission. And then he also believed that in the limit of high temperatures, the radiation density, whatever that radiation density is, which is acting on that atom, will go to infinity. Now, this is something about which I'll make a remark later on, but this is something which he believed. So the fifth assumption is that at temperature T, the population or probability of levels with energy E is proportional to the Boltzmann factor. That if there is an energy E in some level at temperature T, this should be the probability with which it occurs. This is a very strong thermodynamic, statistical, mechanical assumption, and very, very strongly supported by experimental evidence. This is called the Boltzmann factor, and which is used probably everywhere in physics. So this is not an assumption which is very unreasonable. It is actually a very reasonable assumption. So with these assumptions, he wrote down the probability of the nth level, or a probability of occurrence of nth level, as Pn times e to the power minus En over kT, where Pn is the what is called statistical factor or weight factor of the nth level. It's only proportional to e to the power minus En by kT, so probability will have a factor in front of it. Now, then he believes that there is a spontaneous emission, and probability for transition in time dt is equal to this dw m going to n is some number a m going to n times dt. This is the amplitude for it to decay from m to n. This he gives an example like the radioactive decays. This is something which it automatically decays in time dt, and induced emission, which also helps in transition from m going to n, that is dwmn is bm to n of dt. And the induced absorption transition, this is also in the presence of radiation. This is equal to dwn equal to bn to m. There is something which you should multiply it with the intensity of radiation, which is missing here. So basically bn will have a factor of un multiplied to it, as in the next equation I will say. So the point is this, that this is in thermal equilibrium, the transition absorption from n to m should equal the reverse transition from M to N. M is the higher level, N is the lower level. And this quantity Pn e to the power minus En over kT into Bn going to M into U nu. Please remember that the induced transition, that is induced emission and induced absorption, they have to be proportional to the intensity of radiation which is causing that. So they were missing here in this factor because of the typo, but you can multiply B with these. So the B's for the induced absorption is equal to induced emission. That is the condition for thermal equilibrium. And he also now uses the fact that for large T, that is fixed nu, but large T, U is large, so therefore A can be neglected. So he takes the limit if you were to use at very high temperatures but fixed frequency, then this term can be neglected, and the two, since T is very high, these exponential factors become equal to 1, and you have Pn Bn going to M equal to Pm Bm going to N. So you can equate these two factors, you can put it there for all, because they don't depend on temperatures, they are atomic variables or constants. Then Bm going to N and multiplied to P will cancel on both sides, e to the power Em minus En by kT minus 1, because this B has been brought to the left hand side. This is equal to Am going to N. And this, if you divide it, will give you the value of U, because U is multiplied by this factor, so you divide it, and U nu is equal to Am going to N, Bm going to N dividing Am by N, and in the denominator you have exponential of Em minus En divided by kT minus 1. This you can compare, because this is the Planck's law, provided this Am upon Bn, this is equal to 8 pi h nu cube over c cube. So you get Planck's law out of the thermal equilibrium, that one is, having the incoming intensity of light that is causing the transitions, and that fixes the intensity of light to be exactly that of the Planck radiation of frequency nu. And further, the frequency nu has to be equal to Em minus En, because in the Planck's law, Em minus En is equal to h nu. So this Em minus En is fixed as h nu. So by a single equation for thermal equilibrium, Einstein obtains two things: one, the Planck's law, and the second, the Bohr's condition of frequency condition. This is a remarkable paper, because then it tells us how the emission probabilities are connected to absorption probabilities or induced probabilities, induced absorption or emission probabilities. So that is something which A's and B's are connected with each other. Now, after this, this was 1917, Einstein's paper is 1917, and 1918 to 1925, there was a great confusion and great attempt made by extremely large number of scientists, because the major problem at that time was how to explain radiation interacting with atom. People thought that if the atom contains only frequencies, the energy is like E1, E2, En, and their differences give us the frequencies, that is Em minus En divided by h. So one should be able to obtain a picture of some kind of an oscillator sitting inside the atom, oscillating with that frequency. So you can replace the atom with a very large number of oscillators, each of which have frequencies related to the differences of energies. Okay, so you have H nu Mn, H is missing here, which is Em minus En. So the differences of energies determine the frequencies of oscillators. Now the question one can ask is, how many oscillators are there? And after all, if in an atom like hydrogen atom there is only one electron, so where are these oscillators? What are they doing? And how it is that this single electron can oscillate with all these differences of frequencies, which was extremely confusing thing. And the classical theory, if you try to use, then if there is a process with frequency nu, frequency, let us say nu or omega or whatever you use, then this periodic process will expand, will expect you to have all the higher harmonics of that frequency. That is, any quantity dependent on t will be expanded in a Fourier series in which not only e to the power I omega t will appear, e to the power 2i omega t, 3i omega t, etc., etc. So the frequencies will be omega, 2 omega, 3 omega, 4 omega, etc. Now that is not what is happening here, because you see only frequencies which are in the differences. You don't have Em minus En multiplied by 2 or 3 or 4 as the possible frequency. You can just look at the spectrum and see that you cannot have, these kind of regularities, that you have E1 minus E2 may be there, but 2E1 minus E2 may not be there, and so on. So this is something which is very fundamental, and this is what made Heisenberg and of course others. There are Ledenberg, Kramers, Heisenberg, and Slater, and Niels Bohr. All these 4 or 5 people, and later on Born and Jordan, they all were working on this, how to explain this. And Heisenberg clearly, at least Heisenberg as well as Born, they realized that every quantity should be written as a combination of all these differences of frequencies. That is, you write it as x mn e to the power omega mn t, but don't write it as 2 omega mn and 3 omega mn, etc., etc. So every quantity which can be expanded in a series, it should have all the possible differences of energies as the possible frequencies and not their harmonics. That is the important point. So omega mn here is just the Em minus En by h cross, and you run over all m's and n's, and this is expression for every physical quantity. Just x is not just position, but it could be momentum, x dot, etc., etc. And the second point is that omega mn, if added to omega nr, will become omega mr, because obviously these are differences. So when you add the two differences with one of the frequencies common, that will cancel. So the classical formula might have looked like this, where it is x alpha e to the power I alpha omega mn, and for each frequency difference you will have enormously large number of multiples or harmonics of that frequency, but that is not the case here. And so every quantity is then represented by a quantity which has two indices in it, corresponding to the difference of frequencies between Em and En, and therefore it is a matrix. And if x is a constant, then obviously you can see there is no time dependence, so there will be a omega mn where m not equal to n. Those terms are missing, so those quantities will be there. So it will be a diagonal quantity, which is x mn equal to 0 for m not equal to. Also, if x is real, then you can see from that above equation, you take the star and compare the coefficients on the same side. Then on the two sides, the coefficients of e to the power I omega mn, then you'll find that x star of mn is equal to x nm. So these are the kind of things, because em minus en, when you take the complex conjugate, will reverse its sign because I becomes minus I, and therefore when you equate, this will be the condition. So it's like Hermitian condition. Also, if you take product of two quantities, then that will be represented by xmn yrs exponent of I omega mn omega rs t, and this obviously is not of that form with which you want to show every other quantity. Of course, out of the four summations, one can be eliminated because omega mn plus omega ns is equal to omega ms, but there is still one more summation. So that you force it and you make this law that products will contain only those terms which will again be of the standard form, in which there is a coefficient for each omega mn. That gives you that these x and y will multiply like matrices. So I cannot go into all the details, and it is extremely fairly complicated, that it will be the kind of matrix mechanics which was developed, and how eventually they were able to solve the problems of intensities through the dispersion theory, that is through the theory which was being developed by these people. And these today you will be able to understand it because the quantity x that is being talked about here, if there is a charged particle, we know that the radiation from that charged particle will be proportional to the dipole moment square, and this x is occurring there, so multiplied by charge it will give you the dipole moment, and the intensity of light will be proportional to the square of that, etc., etc. So intensities could be calculated, and eventually, as you know, quantum mechanics did find its could explain all the spectra. Now this is the matrix mechanics. I have just done no justice at all, but only told you why matrices became important in this business. And the other route to quantum mechanics is from the wave particle picture. So wave particle picture is also important, and this is what eventually gave us the Schrodinger equation, and it is in that direction I will go now in the remaining time. So this is something which started with de Broglie's 1924 idea, and that was he's applied special relativity to the to his own idea of simply explaining the periodicity that he thought is there for every particle. Now this is a very strange and completely out of the blue idea, that every particle with a rest mass m0 is equivalent to energy mc square, and therefore he says Einstein's quantum condition would require the frequency nu0 to be m0 c square divided by h. Now this is something which he thought was a periodic motion, therefore there should be a quantity which is exponential of I times 2 pi nu0 t0. Okay, so these are the things which he then tried to see from the point of view of relativity. Now special relativity, you know that this quantity, which is only oscillating with time in one frame of reference, will not be doing so in the other frame of reference, because in other frame of reference time and space will get mixed up. So he writes the same quantity in the other frame of reference, and in the other frame of reference this t0 which was there here in the one frame, the rest frame of the particle, will become t minus vx over c square divided by square root of 1 minus v square by c square. So this, if I write it as e to the power I omega t minus k into x, then it will become omega will be this quantity which is multiplying t, and this will become the x which is quantity which is multiplying x, and the relationship between the two can be obtained by eliminating v between the two. So v is a common quantity which is the velocity of the other frame of reference, and it will give us E square, which is m square c2 power 4, which is a well-known formula of relativity. So the thing is that starting from one oscillatory motion in the rest frame, he goes to another frame of reference, and that oscillatory motion looks like a plane wave in the other frame. And this is what he tried to explain as the matter wave, and with an angular frequency omega and a wave vector k. If you try to calculate the wavelength, then that is just 2 pi by lambda. K is 2 pi by lambda. So lambda will turn out to be equal to h over p. Now, p is the momentum of the particle. If you want to find the phase velocity, omega over k is c square over v, which is obviously greater than the velocity of light. So that is ridiculous. But he gives the argument that if you take the group velocity, then this is what you will get. D omega over dk will be actually equal to small v, which makes it the reasonable thing that the group velocity is where. So all these waves are traveling, and therefore there is a wave packet which has a group velocity, which determines the actual velocity of the particle. Now this is something which therefore experimentally people looked out for this, and there is literature there quite a bit, that experimentally these matter waves were confirmed. Actually, what they did was to bombard some particles with some frequency, some energy, and then pass them through this thing where they would be able to absorb or show how much of the wavelength they had. Those experiments I am not discussing here for want of time, but this is something which is well known, and you can check for it. And the last thing that I want to discuss today is the Schrodinger's contribution, which was again a very, very interesting thing. Schrodinger, there is a 1926 paper whose title is Quantization as an Eigenvalue Problem. And quantization as an eigenvalue problem, he came to think of this, that even in classical mechanics, there are situations where quantities which ought to be continuous are not continuous, like vibrating strings or resonant cavities, which have particular standing waves or waves which are there for only some specified wavelengths or frequencies. So this is something which he wanted to apply and think of some kind of an eigenvalue problem or a vibrating string problem for quantum mechanics. And this the interesting point is that he did derive this equation. Of course, I have been talking about it. All the universities in MSc level, they usually ask what is the derivation of Schrodinger equation. Obviously, there can be no derivation of Schrodinger equation, because anything new does not come like a deductive logical result. But Schrodinger did have some way of arriving at that equation, and that is what we are saying. It's not as if that can be justified too much. He starts with the Hamilton-Jacobi equation. That is, the Hamilton-Jacobi equation, as you know, is you write the Hamiltonian in terms of coordinates and momenta, and each momentum is then written as a derivative of this quantity S, which is called the principal function or the action derivative with respect to Q. And this, for time-independent Hamilton-Jacobi equation, is just H is equal to Q comma ds by dq equal to E. And he writes S equal to K times log of psi. For K, he gives the explanation, since S is a quantity of dimensions of action. Remember that S is obtained by the integral of L dt, the Lagrangian integrated over time. So it has the dimensions of action, and that is equal to K times log of psi. And he says that since action gets added up we are looking for a quantity which for different degrees of freedom or independent these things will get multiplied. So it's an argument of the same type as you give for entropy, where entropy is written as something which is constant times the log of probabilities. But here psi is not probability, but it's a function. So when he multiplies and substitutes there, let's take, for example, the hydrogen atom for which he solved this first, that H is p square by 2m, p vector square by 2m minus e square by r, where r is under root of x square plus y square plus z square. Then for I, the expression, this is d psi by d x whole square, p square by 2m. For p, you write ds by dx whole square, and you are multiplying by 2m on the right hand side to everything, minus e square by 2m, and then you bring that e, which is here, on the left hand side. So everything on the left hand side is equal to 0. This part, the right hand side of this I, this is an expression of Hamilton-Jacobi equation written in terms of not s but k log s. This is equal to 0, so it doesn't mean anything. But what he says, the Schrodinger says, is that this is equal to 0 in classical mechanics, but actually what we should be doing is to take this entire thing and treat this as a Lagrangian over the volume and try to find the minimum or extremum of this, just as we find the Lagrange, the extremum of the Lagrangian and obtain the Euler-Lagrange's equation. So you forget about this 0, take this whole quantity and integrate it over. So take I and multiply it by d volume of this thing, and then find the Lagrange's equations for this. And that equals, if you write di over d psi minus d by dx of di over d psi by dx, and similarly for y and z. This is the Lagrange's equation for this quantity I. If you take that quantity I, then the equation that you will get is minus k square over 2m del square psi minus e square by r psi equal to e psi. This is the eigenvalue equation that he is looking out, and then by solving it and then comparing it with the values, you find that this k square should actually be equal to the h cross square. So you get the Schrodinger equation out of a quantity which has its let us say origin in the Hamilton-Jacobi equation, and that is how he got the Schrodinger equation. I think I'll stop here because one can go on. This quantum mechanics is still developing even today, and the 100 years of history is there. But this, I hope, is enough to give you an idea of these ideas or history of these ideas. And the most important thing is to read some of the original papers today, which are simpler to read because you already have learned quantum mechanics, and then to appreciate how difficult it must have been to get this kind of knowledge. Most students I have taught, they are unable to understand how out of nowhere you just produce a Schrodinger equation and say that you solve it, you will get the energy eigenvalues. Or if you tell them that there is a Hilbert space and there is an operator and every quantity is given as a self-adjoint operator on that Hilbert space, that is too abstract and that doesn't know. So one way to get out of the uneasiness that you feel in quantum mechanics is to read its history as much as you can. And I have a set of references which I will probably send to Professor Vijay Raghavan. You can get it from there. A list of references where you can read all this material if you are interested, and don't try to read it like a serious course, but over a period of time in small bits and pieces and by thinking about it. Thank you very much, and I suppose I have just finished in good time, 45 minutes. So I'll leave it for students to ask questions.
Sir,
Yes.
excuse me, sir.
Yes.
Sir, I have a question, sir. Sir, how did Bohr derive the value of angular momentum for an electron, sir?
Angular momentum was already people were talking about, because angular momentum has the same dimensions as action, and this so-called quantum of action, that everything is is in units of h, was there already. So if you have a
Yes, sir.
circular orbit, you can, yeah.
Yes, sir. We know that the angular momentum should be the integral multiple of Planck constant, sir. So
Yes.
how can we express that, sir, without the idea of matter waves?
No, it is possible. You see, if you read the history, you will find that everybody was confused, but they all knew that classical mechanics is not a correct theory. So they were trying and guessing. It is not something which you can explain logically. Okay. So this is something which people said, okay, H is a quantity which is leading to quantum. A lot of people were thinking that, energy comes out in lumps, but nobody believed that lumps of energy can carry momentum. Even Einstein, he gave the idea of a photon or quantum of a light, and from 1905 to 1920 or some such thing, he still did not talk about momentum of the photon. So it is very surprising. He definitely says there are no spherical waves, but he was very careful about not saying that it carries momentum. So this goes on. Only in 1921 he says it is equal to h nu divided by c, basically the energy divided by the velocity.
Okay, sir. Yes, sir. The Bohr proposed the theory, sir, before introducing the matter wave concept. But
no, matter waves
only
were
realized after.
Yeah, matter waves were proposed by de Broglie in 1924, much later.
Yes, sir. Before that, Bohr atom model was published.
Sure, 1913.
But yes, sir. We understood the wave mechanical concept of an atom
Yes.
by the concept of matter waves.
Well,
sir, I have a question that, sir,
yeah.
how to understand the concept, the MVR equal to NH divided by 2 pi, without the idea of matter waves. That is the lambda equal to H over MV. That means 2 pi r equal to n lambda.
Yes, yes. I do not know exactly, but because nobody knows what was going on in their mind. So all that they thought was that there is a electron as a point particle moving in a circle of 2 pi r. It has velocity v, it has mass m. So m times v times 2 pi r should be equal to some integral multiple of h. That is the idea they had.
Yes, sir.
Pankaj, I have a question.
Okay. Yeah.
Who brought in the idea of momentum for photon, and when was this exactly?
Momentum per photon, Einstein himself talks about it, I think, in 1921.
And when was this Compton effect?
Compton effect was slightly later.
Right.
Just around the quantum. Compton effect was, I think, 1925, 94, 24 or some such thing. After this.
Yeah, of course.
Hmm.
Of course, one has to know about momentum, and then only that all
Correct.
that.
Right.
So which paper of Einstein is this?
This 1917 paper.
No, momentum.
Oh, I'll have to look up into the book. Yes.
Fine.
But it will be mentioned somewhere in, if you have Abraham Pye's Subtle is the Lord, then it is mentioned in those chapters where he discusses Einstein's contribution to quantum theory. But I can send you the reference.
Okay, fine. Thanks.
Yes, Professor. I think a majority of the participants, they are also requested through our WhatsApp group.
Yes.
So what are all the references books for the basics or advanced level quantum mechanics, sir. They asked.
Okay, I'll send a list of references to Professor Vijay Raghavan, and
Yes, sir.
then he can continue, put it on
Yes,
WhatsApp
Professor.
or wherever.
Yeah.
Okay.
Thank you, Professor.
All right. Thank you very much. I enjoyed doing this.
Yes, sir. Yes, Professor. Thank you. Thank you so much, sir. Dear participants, I think so. We have end of this first session now. I think Professor Pankaj Sharan's lecture is over. 4 lectures, I think, which may be very much useful. Sir, we got the feedback through our quantum mechanics groups. This lecture, which is very much useful for them. Some of them are interested to do the research, theoretical physics. I think it is motivated for them to do the research in the theoretical aspects.
Okay.
Thank you so much, Professor.
Okay. Okay. Thank you all.
Dear participants, the next session is we have around 11:30. Professor Ashok Kapoor sir, can we check it again today?
We will check right now.
Yes.
I want to try out.
Participants, you may leave now. You can rejoin 11:30. Thank you.
Yeah, I would like to check a few things again.
Yes,
because
sir. Yes, sir. We are here only.
Huh.
I requested the participants that they have to rejoin again 11:30.
Okay, fine. So I will share the screen and try out things.
Yes, Professor.
So it says share a window. It doesn't share the screen. So when I have to switch between windows, I have problem.
Oh, okay, okay, okay. Are you
Advanced.
using a desktop, Professor? A desktop or a laptop?
This is a laptop.
A laptops. Okay.
It says then advanced option. It says portion of screen, computer audio, content from second camera.
Okay.
So I will just try out desktop.
Okay, sir. Okay, Professor.
sharing
We'll try.
desktop, sharing desktop 1. I will try out and see whether this works. Okay.
Okay,
So
sir.
let me. I just want to switch between 2 windows. Are you able to see this window where I have answers for quiz 5?
1 second.
Are you able to see this window?
Yes, yes, Professor.
Answers for quiz 5 from problem set selected for workshop.
Yes, Professor.
You are able to see. And then I minimize this and you are able to see this probability average value question.
Yes, yes, Professor.
Then this is fine. This is all I wanted to check.
Problem
then-
to be solved. We are seeing now problem to be solved.
Problems to be solved. And then there is a second screen. This is my Mozilla screen where I have something on internet which I will discuss.
Yes, sir.
So, but I have another problem. See, I leave it like this. When I come back
Yes,
and
sir.
when
Yes, sir.
somebody is talking, I am not able to hear.
Okay, sir. Okay, sir.
I don't know why that happens. But anyway.
Oh. Now, can you hear, Professor? Can you hear
Right
my
now,
voice?
Yes, right now I can hear you. But this
Yes,
does
sir.
not.
We'll leave as it is. We'll start from here.
Just one moment. It does not seem to work the way I expect. Maybe maybe my internet is slow. Okay, fine. This is okay. We'll leave it as
Yes.
it is.
Yes, sir. Yes, sir.
Yeah.
These are all the answers for the quiz. Yeah.
Yeah, this is only one quiz which they have submitted online. So I
Yeah.
will tell the answers first.
Okay, sir. Okay, Professor.
Some 20 participants have submitted their responses.
Okay.
So I will discuss the answers, show them some data, statistics, and so
Okay,
on.
sir.
We
Okay.
will start the session. Okay, thank you.
Thank you, sir. Thank you.
हेलो, हाँ पंकज, ये हमको ये पूछना था कि एरेनफेस्ट वाज द वन हु प्रपोज्ड एंगुलर मोमेंटम क्वांटाइजेशन. हाँ तो but because in whatever I have seen, this is not mentioned anywhere. अच्छा. Okay. Hmm. I see. Oh, that is very interesting. And then this Einstein, because I could never figure out who gave the expression for momentum. Einstein should have given earlier. He gave the relativity theory, and this is amazing. ऐसे? अच्छा. हाँ. I see. I see. हाँ. Hmm. 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 And one more question. Schrodinger himself is supposed to have discovered Klein-Gordon, worked on Klein-Gordon equation first, relativistic equation, and then discarded, then he came to this. That part is not recorded well. But it is not, and there is no reference for this. I just see this as a statement. देख के या बताना सब points पे. And whatever you write, you send. I am going to put it on zero space. So you write it from that point of view. Okay. ठीक है. Okay. Good. Bye.
रेखा जरा नीचे आओ. आई ए मिर्ची कहाँ रखी है? मैं बोली थी बॉटल के भरी नहीं. अब खाना खा के पेपर वाले में वो नहीं दूसरा एक और था ना पूरी थी. ये तो जो चेन्नई में खरीद के रखे थे वही सब चला।
चंद्रमा नहीं आए क्या आज? बोलो बोलो।
उनका पैसा आ गया नीचे वाला।
हाँ
उसमें एक सब्जी होगी, मुझे तो खाना नहीं है। लौकी की सब्जी, लौकी कटी कटी खराब हो गई है वो।
Professor, can you hear my voice?
Yes, sir.
Ah,
Professor, can you hear now? Professor Kapoor, sir?
Hello.
Sir, Professor, can you hear?
Yes, I can hear you, but I'll use headphone. Then I will test once again.
Oh,
Shall
okay.
we?
Sir.
Shall we start?
Yes, Professor.
I use
Sir,
headphone.
can we wait few more minutes? I think participants are joining.
That is okay. I will meanwhile try out headphone.
Yes.
Then there will be very little disturbance. Okay. So
Okay.
let me just check headphone, speaker and volume, etc.
Yeah, now your voice is clear, sir.
No, but there will be outside disturbance. Headphone. Can you check this volume now? Is it okay?
Sir.
Is the volume of my voice is okay? Can you hear?
Yes, Professor. Yes.
Okay, fine, good. This is all that I wanted to check. Whenever you want, you just tell me. I will start.
Okay. Okay, Professor. Sir, can we start, sir? Professor?
Yeah, can you hear me now?
Yes, Professor.
Yeah, my mic was muted, so.
Yeah. So you can start, sir. We'll
Yeah,
start.
I will start, yeah. Last time we discussed postulate, especially postulate number 3, how it can be used to calculate observable quantities. I will come back to that in after a discussion of a quiz which has been submitted by several participants online. This quiz was part of a problem sets I have selected, and I have asked people to submit their answers because it was fairly straightforward thing, nothing new was involved.
Okay.
It was about free particle. You can see the quiz on my screen, I suppose. The screen, and these are the answers. The questions are also here. So I'll discuss this, and then I'll go back to postulates and discuss some selected problems. So the quiz, this is answers. Answers I have are all hidden here right now. Only you can see only questions. Okay. So I will discuss these answers, show you some statistics, and then go to other problem sets. So the question was several statements about the wave function of a particle are given here. In the blue, the question is written. For each question, for each case, find out if the particle must be free particle. So there are 6 statements here. So question number 1, statement number 1 is Schrodinger equation, time dependent, eigenvalue equation. Question number 2, the wave function satisfies, this is repeated, I am sorry. Why is this repeated so many times? I will show you the question paper. I'm sorry, there is a mistake here. Okay, the answers are okay, but I'll get you this is has not been double checked, typed by somebody else. So I will show you the questions. Questions are in this set, problem number 5, problem set number 5.
Yes.
Yeah, so this is the same question which I was talking about. The first question is, suppose the wave function satisfies the eigenvalue equation, energy eigenvalue equation, that is important. Then is it a free particle or not? That is the question. And people have to write true or false. True if it is a free particle, false if it is not a free particle. Similarly, other statements. Suppose the wave function is a Gaussian wave packet. Must the particle be free, or is this statement true or false? So does this imply, similarly third and fourth and fifth? Third statement is the wave function is given to be a sin x plus b cos x. Does it imply that the particle is free? And again, the answer is expected true or false. Then plane wave. Then satisfies the time dependent Schrodinger equation. Okay. If the particle satisfies time dependent Schrodinger equation, does this equation imply that the particle must be free, or does it not imply? If the wave function is normalizable, then does it imply that the particle is free or not? So people have to submit the answers online in a Google form, which I will show you. First, I want to discuss the answers, so I have to keep this open because there has been some mistake. I don't know what happened. Somebody has typed and but the answers I have typed. So
Yeah.
answers you can see. Leave out the questions. You can read the questions from here. The first question is energy eigenvalue problem. Is this? So the wave function satisfies energy eigenvalue problem. That means energy operator is a Hamiltonian operator, and we can see from here the Hamiltonian operator is free particle Hamiltonian. Therefore, this equation will always mean solution of this equation will always refer to a free particle. So this statement, first statement is true.
Yes.
Second statement, don't read the question from here. This question one got repeated everywhere. Is a Gaussian wave packet. A wave packet can be constructed from eigenfunctions of any Hermitian operator. So there is no free particle involved here. If I take any Hermitian operator, its eigenfunctions I can use and construct a Gaussian wave packet. So there is no reference to free particle here. It does not, a Gaussian wave packet like free wave function does not imply that particle is free. There are other reasons, you will see. Then third question. Okay. Third question is a combination of sine and cosine wave function, sine kx and cos kx. The answer is just giving the wave function does not tell us if the particle is free or not. One must have a way of telling the time dependence or the Hamiltonian. There is no other way whether we can define whether we can decide whether the particle is free or not. If I just give the wave function, it doesn't tell me anything. This wave function, no time dependence is known. Okay, so either we should know the time dependence of the wave function, then we can decide based on the time dependence, we can decide the particle is free or not, or we should know its Hamiltonian. It is same thing. There is simply no other way. So here it is given wave function, at some time it is given. Same comment applies to plane waves. This is wave function being plane waves does not guarantee that the Hamiltonian of the system is free in a particle Hamiltonian. If I just know that the wave function is plane wave, it doesn't mean in any way that the Hamiltonian is free particle Hamiltonian. So there is no guarantee. So this answer is false. Okay.
Professor, I have a doubt
Yes.
regarding the third question.
Yes.
Yeah, the linear combination of sine and cos term, no, usually the solution for the second order differential equation is we can use it like a sine kx plus b cos kx. You know?
Yeah, that is there in the question number 1. Yes. It is a solution of some differential equation. But what has that differential equation got to with the system with which we are talking about? If some particle has this wave function, its Hamiltonian could be something else, and it could be evolving according to some other way, some other potential. Okay.
Okay.
This will become clear in point number 4. Again, you can ask same question about 4th.
Yeah.
Okay. So if you have plane waves, for example, I have given more explanation. I have given different explanation for each case. Although basic explanation is just that the Hamiltonian or time dependence must be given. But I have written out several different explanations in each case. Okay. So let us go through this. Question 4. Suppose the wave function is plane wave. Can I say that the particle is free particle? The answer is no. Wave function being plane wave does not guarantee that the Hamiltonian of the system is free particle. So let me just, I have explained it a little more here. It may be the wave function or at some initial time. For example, wave function of an incident beam in a scattering experiment. If we have a scattering experiment, initially the wave function may be like free particle because the system is very far off from potential and potential may be 0. The wave function may be like free particle. But is the particle free when there is a potential energy? The answer is no. So to decide if it is a free particle or not, we must know how the wave function evolves with time. After, if it is the initial wave function for some potential particle in some potential, then after some time it will go in some other direction. It will not behave like a free particle. Question 5. If it satisfies Schrodinger equation like this is time-dependent Schrodinger equation. Right hand side has to be the Hamiltonian operator acting on psi, and that Hamiltonian operator of the system or of the particle is free particle. So we can definitely say that if the wave function obeys this equation, then it will be a free particle. Number 6, normalizable. This has nothing to do with particle being free or anything, because every vector in the Hilbert space is supposed to be normalizable. So you take any arbitrary vector, I don't know what it means. It can be anything, any system. So these are the answers for this. Any questions on this are most welcome. I will show you some statistics after your questions, how people have answered different questions. Any questions are welcome. Again, if there are any doubts or anything to be discussed.
Yeah, participants, if you have any queries regarding this, you can discuss now.
All right, I will show some statistics, how people
Yes,
have
sir.
answered. 20 participants have answered this question. So
Okay.
remember, only answer 1 is true and answer 5 is true. Rest is all false. So answer 1. 30% say false, 70% say true. The correct answer is true.
Okay.
Answer 2, 50-50. It is actually the correct answer is false. Answer 3. Correct answer is false. Here 70% are saying it is true. Answer 4. Again, correct answer is false. Here 40% people are saying it is are giving the 60% are giving the correct answer, which is false. Answer 5. The correct answer is true, but only 45% have said that. Answer 6. The correct answer is false, and only 40% are saying that correct answer is false. So these are the statistics. I thought it will be of some interest to see how people have responded. Some people have given 2 answers and twice. I have not looked at those details, and I wish more participants had responded to this quiz.
Yes.
I just wanted to have an idea how people respond, and I was expecting a better response with respect to question 1 and question 5. Others are a bit confusing, but question 1 and question 5 are very clear that it must be a free particle. Okay, any comments or questions about this? This Google form is a very useful thing for online teaching or even otherwise in classroom teaching. If people are allowed to use their mobile phones, one can do all this whatever I'm showing with the help of students having access to their mobiles in the classroom. Some places don't allow, some places may allow, some teachers may not allow. So if they are allowed to use their mobiles, then whatever we are doing online can also be done in classroom. And it can have some kind of live interaction, and you can show them immediately the results and statistics. All right, so we will leave this quiz here. Yes. I will, by the way, I will also, I think this information must have reached you, but let me just show this. Whatever material I prepare, I am putting on internet. This is zerospace.org. I have sent a link, and I suppose it has reached to your places. Yeah. This is my area. If you click on my courses at different institutions, this link, this page link you must have received. Otherwise, I'll send again. So this particular page is about archives. Archives means the courses which have been given by different persons, and I have collected their material and put here. I am in the process of doing this. So there are resources contributed by Professor Mani, a large number of them. There are many more which have to be uploaded. There are resources contributed by Professor Pankaj Sharan. Again, I have to collect many more and upload them here. These are my courses, and the first line here, it has all the resources which I am using in this workshop. So if you come to this page, you will have access to every resource. Right now, I put the first draft. It will remain here. Whenever I revise the first draft of my lectures, because there are errors, mistakes, and improvements can be done, they will come here as second draft. So if you want access to anything that I have done, you can come to this particular page and expand this list. My courses, my means Kapoor, because this is, I don't have time to tell you about all this website. So if you click at this, the first line you will see is the 4 lectures given at BS Abdur Rahman University, Crescent Institute of Science and Technology. And then this has all the lectures, and you can open. This is a pop-up window. You can open in a new tab or this tab or anywhere or close it. So suppose I open this. From here you can download all the files that I have used. I'll just show you. See here, all the files that I have used so far, they are here. You can, all that can be downloaded. Similarly, other things can be accessed here. I have discussed the postulate consistency of probability interpretation. So that also is available here. Again, you can open in a new tab or same tab. So this is what, no, this we have not discussed actually. If we have time, we'll discuss this. And answers for the quiz which you have just seen, they are also linked here. And I will correct this mistake of all answers being same. This is some copying pasting problem, I suppose, at some stage. All right, I will close this browser window and come back to what we are doing.
मुझे अपना मोबाइल तकिए को लगा दो
लगाओ भाई वो. Okay, so we will now, I will quickly revise the postulates, the third postulate, and then we will go and do some problem solving depending on how much time we have based on the postulates. I also had planned to do problems on time evolution. If the wave function is given at an initial time, how do we calculate wave function at later time? That is related to what we are doing next step, but I am not sure whether we will be able to do that today. So let us see how it goes. If there is time, I will say briefly about that also. So third postulate is, as I said, it comes in several parts. If I have an operator A, its eigenvectors I denote by UK, eigenvalues by alpha k. The eigenvectors are orthonormal. Then first part of the postulate says that if you make a measurement of any dynamical variable A, you will get the outcome of measurement will be one of the eigenvalues, nothing else. So if we want to know what are the results that we are going to get after measuring the particular variable, we must calculate the eigenvalues of the corresponding operator. Then next, okay, then okay, sorry, there was some disturbance. Then when suppose we know that in a state a particular dynamical variable has a definite value alpha n which must be its eigenvalue, then we can definitely say that the corresponding state is represented by its eigenvector un corresponding to that value alpha n, and vice versa. if we know that the state vector, somehow we know, we have given this information that the state vector is un, an eigenvector of a measurement of a will give you that value alpha n definitely. What happens if there is a linear superposition of different eigenvectors? If I have only one eigenvector that is represents the wave function or the state of the system, then it is clear. There is no confusion, no doubt, nothing, no ambiguity. But if I have the state vector given as linear superposition of two different eigenvalues, eigenvectors, then what happens? Something like this. In that case, the answer is sometimes you will get value alpha 1 and sometimes you will get value alpha 2. If we make several repeated measurements, we will get value alpha 1 with probability of modulus C1 square and value alpha 2 with probability modulus C2 square. I have written it out for 2. We can have any number of them here. The similar statements will apply. Okay. Remember, the main point here is that one has to make, to determine the probability, one has to make several repeated measurements. Okay. Or measurement of several copies of a system, identical copies. A single measurement will never, we can never predict what is the outcome going to be. And that is what the indeterminacy of quantum system is about. So this is the third postulate. Fourth postulate is, fourth part of this is just what I have said. The probabilities are proportional to the coefficients of expansion. Now, how do I apply this postulate? Suppose the state vector is given to be some ket psi, which is not linear superposition, then you have to write this first as a linear superposition of eigenvectors. And when you are writing this, everything should be normalized, then the probability will be proportional to Ck square. Probability of alpha k will be proportional to Ck square. If everything is not normalized, then the formula will be more complicated. I have not written out, but it can be worked out. The best thing is, when you are calculating probabilities, first normalize everything. Okay. So these are the 4 postulates. This is the third postulate. And then how do we calculate probability? Most of the time we need the coefficient in the expansion of psi. I said write psi as a linear superposition of eigenvectors of A, which is being, the A is being measured and we want probabilities of different results. So we have to get hold of this coefficient Ck. That's very easy because Uk is the eigenvectors are orthonormal. So if you just multiply by something, you will get that particular coefficient here. That is what is written out here. If I multiply by Uk psi, take this scalar product, that will be just this coefficient Ck. Please remember, do not forget, otherwise there will be mistakes. You will get nonsensical answers. Everything has to be normalized. So this is the final formula that is needed. And then I have made some consistency checks, which I will skip. That what tells me that the probability should be add up to 1, that is Parseval relation, and so on. I will now come to applications of these to problem solving, because problem solving, it helps us in fixing our ideas. And the problems that I take are very simple to begin with. They can be made more and more complicated. That is not the issue. If we understand in simpler context and understand it well, you can always apply it to more complicated problems. All right. So I will come to questions. This is the same thing as what I am going to show, but in a slightly different format. This particular set is given as example in the problem sets which have been calculated. I am going to look at the same thing at one by one, not all of them together. This can get, so we will focus on each of these statements one by one, and that is here. Okay. So the first statement is, I am given this. This is the system. The system that I am interested in is a particle. Let me make it bigger because This may not be visible very clearly to everyone, and trim the margins. I suppose this is all right. So the system that I am considering for purpose of these applications is a particle in one-dimensional rigid box. Potential well, we have discussed. I have summarized the results for this. The normalized eigenfunctions are u and x, square root 2 by L sin k and x. Kn is n pi by L, and eigenvalues are h cross square, kn square by 2m, n square h square over 8ml square. So this is the system about which we will be talking about in these examples just now. So keep that in mind. Now, all the next 4 examples are about this system only. And we'll see how postulates are applied, and we'll build it up slowly. Okay, not too steep. So the first question is, if the wave function of the particle is this, what will a measurement of energy give? So you are supposed to write, the person who is attempting this is supposed to write answer here. So this is just the eigenfunction of energy. And what is the particular n value? N value is 17. If you compare with the wave function, kn is n pi by L. So if I take n equal to 17, this is just that eigenfunction. So energy corresponds to 17, n equal to 17. So 289 h cross square over 8 ml square. So that is the answer here. It is fairly straightforward, and that is what you will see here. So the answer to the first part is this. You can now read what is given, what is the question, and what is the answer. This is the simplest application I can have, because the wave function is an eigenfunction. So energy measurement will give you the corresponding eigenvalue, which is n equal to 17. If you have any doubts or any questions or any comments, please feel free to interrupt. I'm trying to build it up slowly, okay? It may look all too trivial, but you'll see that one can build up very slowly and get to more complicated things. Let us ask the converse question. If energy is something else, let's say 121 by h square over 8 ml square, what will be its wave function? Of course, the wave function will be, this is an eigenvalue, then the wave function will be the corresponding eigenfunction. So which eigenvalue it is? N equal to 11. So the wave function will be corresponding wave function n equal to 11. So that answer is, I have written out here, that you see here. If the energy of the particle is known to be this, then the wave function will be, we can definitely say that the wave function will be sin 11 pi x by L. All right, let us proceed. Make things a little more complicated. Suppose I say that the state of the particle is absented by this linear combination. Now there are three terms, some complex coefficients. I have intentionally made it a bit complicated by putting complex coefficients. But what you have to recognize, and then question is, the measurement of energy will result in one of the 3 eigenvalues. What are those 3 eigenvalues? And what are the probabilities? Okay. And what will, you can tell either probabilities or the ratios. So suppose we can read off the probability ratios immediately. Then we can write down the probability. So that is what we have to do here. So first thing we have to do is to recognize that these 3 sign functions are the eigenfunctions of the energy of the system that we have chosen. This one corresponds to n equal to 3. This one corresponds to n equal to 10. This one corresponds to n equal to 29. I have intentionally selected some arbitrary, strange looking numbers here. It doesn't look very simple. So if a wave function is something like this, if a measurement of energy is made, I can get only 3 answers corresponding to n equal to 3, corresponding to n equal to 10, corresponding to n equal to 29. Okay. Any other energy will not be an outcome of measurement of energy if this is given to be the wave function. So one can write down the energy as n square s square over 8 ml square. That is first part of the question. What measurement will result in 3 eigenvalues? Which 3 eigenvalues? Now we want to see probabilities. Probabilities you have to be a bit careful because I have written down wave functions which are not normalizable, not normalized. But normalization for sine 3, sine 10, sine 29, they are equal. So the coefficient squares, modulus squares, absolute squares of the coefficients will actually be proportional to the probabilities. So for probability corresponding to E3 will be 4, probability corresponding to E10 will be modulus square of that is 25. And probability corresponding to E29 will be proportional to 144. So we will get probabilities ratios. Then we can fix the probabilities because there is nothing else possible. All the 3 probabilities should add up to 1. So we can find the probabilities. That is how this example will be answered. And this is fairly easy. I mean, I have taken some time to describe, but you should be able to do it without any difficulty. And everybody who understands the postulates will be able to do it without any difficulty. So the answers are written here. Corresponding to 3, this is the energy. Corresponding to n equal to 10, this is the energy. Corresponding to n equal to 29, this is the energy. No energy, no other eigenvalue will be outcome of experiment which measures the energy. As I said, sometimes for many systems, the normalization of each eigenfunction will be different. Then you have to be very careful. I have taken a very simple example. Normalization is same. So I just take absolute square of these coefficients, 4, and this is 25, and this is 144, 12. So the probabilities will be in the ratio of 4, 25, and 144. All of them should add up to 1. Therefore, actual probabilities will be 4 by 173, 25 by 123, and 144 by 173. Any questions up to this stage? All right. If there are no questions, I assume that everything is clear because everything is so simple. I'll go to the next one, make things more complicated. Now I'm given a different kind of wave function. Remember, we are dealing with particle in a box. So any wave function for that system should be 0 outside the box. So that's why this 0 outside the box is from 0 to L. On the boundary, the wave function should vanish. So it has been chosen that way. X equal to 0, wave function is 0. X equal to L, wave function is L. So this is an acceptable wave function for the system that we are talking about. So that check should be made. If I have written it carefully, it is fine. If somebody makes a silly mistake, write some arbitrary wave function, then that check has to be made. The question itself doesn't make sense. All right. So now the question is, if I make a measurement of energy, what is the probability that I will get an answer En corresponding to the quantum number n? What will be the probability? Because in general, now we will get all possible energy as a result of measurement. So we want to calculate probability. So what is that we have to do? We are asked to calculate probability, and just now, a little before, we have seen we must write this wave function which is given to us. See, here we are lucky. The wave function was written as a superposition of eigenfunctions. This was given to us. So we didn't have to do any extra work. We just read off the coefficients. But here we are not so lucky. The wave function is given some function. So we have to first express the given wave function as a linear superposition of eigenfunctions. Calculate the coefficients. Once you have calculated the coefficients, then the coefficient modulus Cn square will give you the probabilities. But you also have to check that psi x is normalized or not. So you have to fix this normalization factor n
by demanding that psi x should be normalized. So I will show you not full answer, but I'll show you how it will be done in the second sheet. Okay, so this is the given wave function. So we have to expand psi s in terms of eigenfunctions of the particle in a box. And eigenfunction, nth eigenfunction is sin n pi x by L and square root 2 by L. This is the normalized eigenfunction. If I write normalized eigenfunction, the coefficients can be calculated simply by multiplying by eigenfunction and integrating. So these are the coefficients. These will give you the probabilities provided we fix the normalization correctly. So normalization of psi x will be fixed by a condition which I have not written down. Okay, it is here. 0 to L modulus psi square dx equal to 1. This is 0 to L because outside 0 to L, outside the box, the wave function is 0. So limits are only from 0 to L. Limits are not from minus infinity to plus infinity. Usually the limits will be from minus infinity to plus infinity. All right. Are there any questions on this? Then we can take questions now. So this is the general scheme for calculating the probabilities. If question is simple enough, we can read off the answers immediately. If it is more complicated, then calculations have to be done. So this integral is fairly straightforward and can be done, and answers can be found. Now this process can be repeated for any system. Any system, if I have harmonic oscillator, if I have a free particle, or any system, if I have, I should know. The question is about which particular variable. I should know the eigenfunctions of that variable. Like here it was energy, we could ask for probabilities of measurement of angular momentum or some other variable. So we should have to know eigenfunctions and eigenvalues of that, and then the process is same. Okay, so are there any questions so far? This is fairly simple example, but I thought I'll start with the simple example only and build it up. Okay, I think then let us proceed. How much time I have? This is an exercise I have not solved, but we can. Yes. Yes, please go ahead.
Hello, sir.
Yes, please tell me.
Determine the normalized eigenfunction of the Hamiltonian psi n of x determines
Can you please repeat?
psi n of x.
No. See, what is your question?
Postulates using.
I am not getting your question. What is your question? Can you go slowly? Talk slowly, not so fast.
Yes.
Or put in chat mode. I don't know whether I can see. How do I see chat mode? Maybe somewhere here it will come. Yeah, can you please repeat your question slowly, not so fast? Hello.
Hello, sir. Compute P of T any determine the one-dimensional square well, sir. Hello, sir.
Madam, you can put it in the chat box.
And using eigenfunction of the Hamiltonian.
Yes. I
Hello,
have,
sir. Audible?
yes, I can hear you. Let me try to understand. You are saying that I have a system. I know it's Hamiltonian, and I know its eigenfunctions. Then what is the question?
Normalized eigenfunction of the Hamiltonian phi of x.
Yes. Yes.
We have to find out the compute P of t or split, sir.
Complete what?
P of t. P.
What is
Compute P, determine.
what is
P
P of t?
determine, compute P. That is a time dependent version calculated, sir.
No,
Time-dependent
I am coming
version.
to that. Okay. What you are? Let me
Condition
repeat what
using
you
for
are.
time dependent version model is 5.
Yes, I understand. I think what you are asking is, how do I calculate probability at time t? Is that correct? Is your question about
Yes, sir.
the
Yes, sir.
probability at time t? Okay. Yeah, I am coming
Yes.
to that.
Yes, sir.
If you want to calculate probability at time t, then you have to first find the wave function at time t, and then repeat this process.
Yes, sir.
Okay. So I am coming to how we have to find the how we can find the wave function at time t. I will come to that. I just wanted to show you everyone one exercise which you can try it out, and I will not discuss this. There are several problem sets I have collected. So there is a exercise 3, probability and average value, and all this you can do in. And I will not have time to discuss this. I have lost one lecture. I will come straight away to problem of finding the wave function at a time t if we know the initial wave function. So we will come to that, and that will answer this question which is being asked just now. So let me just say this. This will be very brief. I don't have too much of time, but it will be a complete answer. More details I can put up on the website by tomorrow or day after tomorrow. So if we want to know the probability of something at time t, then we have to solve the Schrodinger equation, the time dependent Schrodinger equation, which is here. And this is how we solve this. I will skip the long story. I have summarized this here. Suppose I know that the initial state is eigenvector of energy, then we can write down the answer immediately. If energy is En, then the answer for the wave function at time t is exponential minus I En t by h cos. That is the factor that we have to multiply. This is correct wave function at time t. If the initial, look at the, let me expand. I am sorry, because when I switch to different files, this goes. So let me change the view so that you can more comfortably read the whole thing. I will fit in the page. What happened? Not page. Wait. Yeah. So what is given here is I have 4 examples. Initial wave function is an eigenfunction of energy with eigenvalue En. Then at time t, initial means at time t equal to 0, I am assuming. At time t, this is the wave function. This is very easy. Everyone understands this. If I have superposition of such wave functions, 2 different energies, please, this is a typo, En and Em, or E1, E2, you can say. Then at time t, the first function will come with energy E1, the second function will come with energy E2. If I have several such terms appearing in, for each term, you put the corresponding exponential of minus IEKT by h cross. Okay. So this is the basic rule. Next. So this can be stated, all this, whatever is written as 1, 2, 3 can be summarized in this fashion. Suppose I have a state psi of t0 and I have a state phi t0. Psi t0 goes into psi t at time t. If I start from phi t0, it goes into phi t. So I am considering 2 different situations. Situation number 1, where initial state is psi t0, And suppose I know that it goes, what happens to it at time t, that answer is known. Similarly, another situation, if initial wave function or initial wave vector is this, then this is the answer. If I know these answers, I can immediately say a linear combination will go into linear combination. This means that the time evolution preserves the linear superposition of states. Now, it does not still tell me how to calculate. If I know the initial vector, how do I initial state of the system? How do I calculate the state at time t? But the answer is here. First, expand the initial state like this. That we have already learned when we are doing probability calculation. So first, we have to expand the initial state. I have not written it out. Initial state as a superposition of eigenvectors of energy. So we will know the coefficients using orthonormalization. This is what I was telling here. Where is it? Somewhere when we are calculating probabilities, we are doing that. No. Okay, it is. No, answers. Yeah. Yeah. So this was the prescription for calculating probability. Same thing you have to do when you want to calculate wave function at time t. Same expansion in terms of energy eigenfunctions. Once you have done this, then for each term you put an exponential, I exponential of minus I kt by h cross. So put that extra term, that will give you the wave function or state vector at time t. So that is the prescription I am going to use, and I will show you some examples. Okay. So let me just see where my examples are. I will have to locate. Here. No, this is no, this is also postulates. I think here only there is a solve problems here. So time evolution. This is set number 4. I have written it out as exercises. The first question is actually an exercise. The second and third I have written out full solutions. So let us first go through quickly what is the first question. The first question is in Article 2, Section 2, we have solved some probabilities. We have calculated some probabilities. What are the probabilities we have calculated? With some wave functions. Some wave function was given and we calculated probability. What will be the probability of energy? Now suppose this is the initial wave function. What will be the wave function at time t? I have to put exponential of minus I e17 t by h cross. That is the answer. Similarly, this case, here I have to put an exponential factor minus I e3 t by h cross. Here exponential of minus I e10 by h cross. And here it will be a factor with energy corresponding to quantum number 29. So this should be obvious. I have not tried to write it down because I think you should get used to thinking like this. If you have any questions, please ask. If you want me to go slow, please tell me. But this should be obvious to everyone. Those who are exposed to quantum mechanics, even new students should be able to understand this, and you should have this habit of doing things whatever can be done without writing. You should be able to see the answers. So I will repeat a bit slowly this part again because I have not written it out. Suppose I am given the same system which we have talked just now. I am given initial wave function at time t equal to 0, and we want to know what is the wave function at time t. This is an eigenfunction of energy, so I have to just multiply by a suitable factor exponential of minus I e t by h cross, and e that comes should be corresponding energy eigenvalue. So E17 will come there. If I have several such things, I have to write one different E factor, exponential factor for each one of them. So that is what I will do for this case. If this is the initial wave function, I will have to write separate exponential factors for each one of them. Here energy. Yeah, please. Somebody wants to ask some question. I can't follow your language. Sorry. Can somebody translate? what he's saying?
Nothing, sir. He is just unmuted.
Okay,
I think.
not relevant for this. Okay, fine. So what I'm saying is, if I have a superposition, I can do this. If I don't have superposition, then I will first get a superposition like what I did for this problem. Okay, so that is the idea. So that is how you can solve. This problems. Where are my problem sets? Here. No, these are postulates, problem sets. So the first question is just that go back to example 2, take the wave functions given as a wave function in initial time and find the wave function at time t. So I have just summarized that. I have given you orally, and you should also think like that. One need not calculate everything. But if I have a complicated system, which I have taken a complicated system, we will calculate, and we will calculate everything. So let us look at something which I will come back to question 2 afterwards if there is time. Let us calculate this free particle wave packet. Suppose I have a free particle. Its Hamiltonian is p square by 2m. Its energy eigenvalues are h cross square k square by 2m. We have seen this. That's why I summarized all the free particle spin and everything. Okay. And we are given something as complicated as this. This is the initial wave function at time t equal to 0. Let me trim this view. I don't know. I have to keep doing that. Trim margins. It didn't happen. View mode, trim view. No, then I have to say fit. I think this is the best that one can have. Trim margins, it says. Yeah, okay. So this is the best we can have. I don't like it, but anyway, let us continue. So we are given an initial wave function which looks fairly complicated. It doesn't look very simple like other cases. And the problem is that the system that we are looking at is a free particle. We know the energy eigenfunctions and we know the energy eigenvalues. So basically we have to solve the time dependent Schrodinger equation for free particle. So I will repeat what is done in textbooks. So you will solve, separate the variables by writing psi xt as some function of time and some function of x, and then you will get two differential equations. And this is the free particle equation which I have summarized earlier. It has solutions like this. These are the eigenfunctions of free particle, and these are the eigenvalues. Then this gives you several solutions. For each case, there is one solution of the original equation that we started with, time dependent equation. So these are several special solutions. These are just what I talked about, energy eigenfunctions multiplied by an exponential factor. If this is the initial wave function, then the answer is obvious. But what is the most general solution of that differential equation? We have to take superposition of all such things. Okay. So most general solution is a superposition of these psi k xt, which is what I have written here. Superposition of with coefficients which depend on k. So this is the most general answer that one can have for as solution of time dependent Schrodinger equation. Now we have to handle this. And what is that we are given? We are given the value of wave function or expression for the wave function at time t equal to 0. So let us just substitute that expression for time t equal to 0, which is given to be that wave packet Gaussian wave function, which looked a bit complicated. Okay, so we have to put at time t equal to 0, this is the wave function. So we just put it here. At t equal to 0, this should be this. So we put that in the left hand side. Now this is just what I have been saying. Expand the initial wave function in terms of eigenfunctions of energy. Get these coefficients using orthonormality. So if I have to get these coefficients phi k, because these phi k's are unknown. Once I know phi k's, I know the answer by integrating this. So I am trying to fix this phi k's. And I am trying to fix this phi k's by using the initial condition which is given to us. So I put time t equal to 0, this exponential disappears. I get initial wave function equal to this integral. But this integral I can now solve for phi k because this is just Fourier transform. In more general situations, this will be eigenfunction. We have to use orthogonality. So we take inverse Fourier transform, we calculate phi k. This integral is a standard integral. I am not going to calculate. Calculate this integral, put it here, calculate another integral, you have the answer. The answer is, it is too complicated, but anyway, this is all Gaussian, so it can be done. I am not doing this because we don't have that kind of time available to us. I hope it is clear, but if there are any questions, I will wait for your questions, comments, or anything you want to say about this particular example. I have one more example and sufficient time to go through that, a different example. I have also sent an email saying that if you have questions, if there are sufficient interest, we can have a forum on zero space and you can post your questions and we can have a discussion there. Anyone can participate. The only requirement is you'll have to create an account there, then you can participate in discussion. Reading is not a problem. For reading anything on zero space, you can read. But if you want to post questions, then or post answers or comments, then you'll have to have an account there. I will talk about it separately. Are there any questions on this particular example? I have given the final answer here. Rest is only doing integrals, which I have not written out details. Let us look at one more example and then I will stop. I may overshoot the allotted time a little bit. This is a different kind of example. This again, I have intentionally made it a bit complicated. It doesn't look simple, obvious. I have a spin 1 system. Spin 1 system, there are 3 states and energies are given to be E, E and E minus 3G. I have specified just like that. It may not correspond to any physical system. This is cooked up example. So there are 3 levels. One with energy E, another level with energy E, and another level with energy E minus 3G. G is some constant. Corresponding eigenfunctions are vectors with 3 components. I have given that also, psi1, psi2, psi3. So this information is given to you. Now, the question is, suppose the system is initially at time t equal to 0 in some state like 1, 0, 0. What will be the state at later time and what will be the probability that system will be found in this state? That is the question. Should I repeat? The answer is here. I have written out full solution. So you will see how to get this answer. Here the question is skipping one step. I am not asking what is the state vector at time t. You need that information to calculate this probability. So first we will have to calculate the state vector at time t. And then calculating this probability is taking scalar product with this and taking absolute square. So the second step is simple. First step is it requires work. So I will show you how to do that work. That everything is written out. So the first step is just this. Start with initial vector and write this as a linear combination of the energy eigenvectors psi1, psi2, psi3. So with some coefficients C1, C2, C3. So these coefficients are unknown to start with. But since we are given psi I here, we can fix this coefficient by orthonormality. So multiply by psi1, that will give you this coefficient. Multiply by psi2, take scalar product, that will give you psi2, and similarly for C2 and similarly C3. So that's very easy. I have to take psi I dagger and psi1 dagger, psi I, and I get 1 by root 2. You can read from here. I take psi2 dagger psi I get 1 by root 6. I take psi3 dagger psi I get 1 by root 3. Basically, we pick up the first line here in each first row in each eigenvector. So these are the coefficients. Once we have these coefficients, you put them here. So the wave function at a later time will be, the coefficient is exponential of minus I et by h cross. I have to put the corresponding energies. So what is the energy of the first level? That is given to be E. Second level has energy E. Third level has energy 3E. So for the first term, I put minus I et by h cross. For the second term, I again put minus I et by h cross, same energy. For third one, I put the energy corresponding to the third level. And we have values of C1, C2, C3. Just substitute and simplify. I just substitute values of C1, C2, C3 and simplify. I have taken this exponential factor out for convenience. So then I am left with only this exponential factor, and we can add up the first two terms and write in this particular form. Third term remains as it is. Something is missing here. This should be 1 by 3, this term here. So I know the state vector of the system at time t. But what is the question? The question is, what is the probability that at time t system will be in this state? Some final state is given and I want probability of that. I am not interested in wave function at time t. The question is about probability that the system will be found in this particular state. That's simple. You have to just take scalar product of this with the wave function or state vector at time t. So that's what we do here. Write that, calculate this. There should be a dagger here. No, this is written correctly. So write everything carefully. Take the scalar product, you get this answer. The required probability is given by modulus square of this. So modulus square of this will kill factor of I exponential, and you will get 4 by 9 sine square 3 dt by 2 h cos. Some h cos factors is missing. So this is the final answer. So this tells you how you, in many questions, how you have to get the wave function at times as an intermediate answer and then calculate probability which is being asked. So I suppose I will stop here. If there are any questions, we can discuss this. And yeah, so questions, comments, anything about this second example? The process is same. That's what I want to emphasize. You should understand this. Process is expand this and then expand the initial wave function in terms of energy eigenfunction, put the suitable energy factors, and then start calculating. That's it. If you know the energy factors. If you don't know the energy eigenvalues, then you have to go back, calculate energy eigenvalues also. There are other things which have been given. You can just try them out. If you want to discuss, you are always welcome to send me email. We can discuss this. Or if there is sufficient interest, we can have a discussion, as I said, on internet. The organizers have to tell me. I will create a forum, and that forum can be used for discussion of continuing the discussion about the topics that we have covered, or for that matter, any other topic. Okay, we'll stop here. Thank you very much for the patience. I wish I had not lost one lecture.
Yes, sir. Thank you so much for solving the problems in a neat way. So it is a clear understanding of us, I think, sir. The participants also, they understood, I think. Thank you so much, sir.
Okay, thank you. We'll close the session now.
Yes, participants,
No,
do you have any queries?
No, I am here. As long as you want, I am here. There is no hurry. Yeah.
Thank you, Professor. I think
Okay.
we'll wind up the session, sir.
Okay, fine. I am whichever way you decide.
Yes, sir. I think you already sent that link, sir. We'll. I think the participants should go through the link, and
Okay.
you have all the materials out there. I think you
I
showed
will.
clearly.
Yeah, I am planning to revise everything and put again. So first draft will be available. Revised draft will also be available.
Yeah. Yes, sir. Yes, sir. I forwarded to participants also, sir.
Okay, good. Thank you.
Thank you, sir. Thank you. Thank you so much, Professor.
Okay.
Thank you. Dear participants, the second session is over. The third session of today's fourth day. So we'll meet around 2 o'clock. Thank you. Now we'll wind up the session. Thank you. Thank you, Professor. Get this thing. It's all silent. Okay,